Okay. So main memory. I've already shown you something like this, but this is the on-chip memory. Main memory is over here. It sits off the DRAM interface, and today it's predominantly DRAM. So we'll mainly focus on DRAM because today it's predominantly DRAM. Right? And main memory is controlled by this memory controller, and you have some interface circuitry that controls the DRAM banks. And we'll cover how this is organized and how this memory controller is organized. Ideally, it's always good to, whenever you're thinking about designing a system, it's always good to think about, ideally, what do I want? Right? And then you try to approximate that ideal at the cost budget and energy budget that you would like to, you can have. Ideally, you would like zero access time, right? You'd like to access this memory, grab this data right away. Infinite capacity, zero cost, and infinite bandwidth to support multiple access in parallel. It'd be lovely to get this, right? But we'll try to approximate all of this, obviously. The problem is, ideal memory's requirements oppose each other, and that's why we design different kinds of systems. Bigger is slower, and this is fundamental. Faster is more expensive, and higher bandwidth is also more expensive, although higher bandwidth is a little bit easier to achieve than faster. So bigger is slower because it takes longer to determine the location. Right? Faster is more expensive. Faster is usually dependent on the memory technology, and we'll see very briefly SRAM versus DRAM. I'm assuming that you all know all of this, so I'll go very quickly on some of these things. And higher bandwidth is more expensive because you need to add something to enable that higher bandwidth. You need to add more banks, more ports, higher frequency, or some faster technology, and all of these increase your cost. We'll try to later, in one of the lectures, we'll try to look at how do you achieve the benefit of more banks without adding more banks by exploiting the underlying technology in DRAM. And so that kind of solutions will hopefully lead us to closer to the ideal without requiring the cost of the ideal. Let's take a look at DRAM very quickly. This is dynamic random access memory, and capacitor charge indicates the stored value here. So whether the capacitor is charged or discharged indicates 1 or 0. And there's obviously a threshold value here, and as that charge window reduces, it becomes much more difficult to sense whether it's a 1 or 0. And that's the fundamental problem with DRAM. So you have only one capacitor. That's really the memory technology, right? Everything else is really peripheral. You need an access transistor to access that charge. And to control that access transistor, you need a row enable signal, which is also called a word line. An address is decoded, and that way you can address this bit, address that capacitor over here. And this bit line is needed to sense this charge or store charge into the capacitor. And that's connected to a sense amplifier and driver circuitry that's down here. So we'll look at that a lot in this. We'll look at this a lot in the next 2 lectures, today and tomorrow. One issue is the capacitor leaks through this RC path. Its charge leaks through that. As a result, DRAM cell loses charge over time. And DRAM cell needs to be refreshed. And this is a fundamental problem with DRAM. And if you have to do one reading for tomorrow, I'd encourage you to do that. We'll talk about how to actually get rid of some of the unnecessary refreshes. SRAM is fundamentally different. I'll just cover this just for comparison purposes. SRAM is not used for main memory technology. It's static random access memory. Basically, it has 2 cross-coupled inverters that store a single bit. And this is the memory cell itself. Everything else, again, peripheral. This feedback path enables the stored value to persist in the cell. Right? To be able to read data out of the cell, basically, you need these access transistors. In this case, you have 2 access transistors, bit line and bit line bar, and you can have differential sensing at the bottom. The word line is very similar to DRAM. Bit lines are, again, very similar to DRAM, and you have some sensing circuitry down there to sense this data. Phase change memory is, again, similar in some sense, right? It has some storage element over here. Basically, the storage element stores data not in terms of charge. Here, we're trapping charge somehow, right? We're trapping charge either in the capacitor or in this cross-coupled inverter. In phase change memory, which we will cover later on, the storage is based on the state of this material. You have this phase change material, chalcogenide glass, which is actually in your optical drives, CD drives. Your CD is like that. It has 2 states, amorphous and crystalline. And by injection of currents in different ways, you can change the state of this element. And the state can be highly resistive or low resistive. And by detecting the resistance of this material, you can detect whether it's a 0 or 1. Again, this is a memory technology. This is the storage element. everything else is peripheral, right? This is the access transistor over here. You have a word line. This is not the best picture over here. We'll look at a better picture. But you have an access transistor as well as some sensing circuitry and a bit line. Okay. The fundamental concept in all of these memories is banking, right? You basically take these cells and you put them together and you form a bank. Actually, you can form a single monolithic array, right? You can basically put these put these things together, right? The problem is if you keep the size of that large, if you make a single monolithic array of these cells, that becomes very long to access. So people bank memories. Basically, you don't want a single monolithic array. It takes too long to access, and it doesn't enable multiple access in parallel. As a result, to reduce the latency of memory array access and enable multiple access in parallel, people divide the array into multiple banks that can be accessed independently. Right? You have either in the same cycle or in consecutive cycles. And we'll look at this a lot. I just want to give you an idea of what is banking. Each bank itself is smaller than the entire memory storage that you have, and accesses to different banks can be overlapped. An issue in this kind of system is how do you map data to different banks? Right? Ideally, if you're accessing multiple things together, you would like those data to be in different banks such that you can get the data quickly in parallel from those banks. But that may not always be the case. How do you basically interleave data across the banks affects how much parallelism you get out of the memory system. So let's take a look at the memory bank organization. Again, this is independent of the technology if you look at this. A memory bank looks like a two-dimensional storage array, and each element in this array is essentially the cell that I showed you earlier. It could be the SRAM cell, it could be the DRAM cell, it could be the phase change memory cell. Basically, this is divided into rows and columns, and to access a row, you need to decode the row address, and to access a column within the row, you need to decode the column address. Basically, to do an access, a row address is decoded, and an entire row of memory is brought down into some place over there, sense amplifiers, and these selected bits drive the bit lines. You get the entire row. Something down here amplifies that row data such that you know whether these are ones or zeros, and later the data that you need is actually decoded. Which column within that row is needed is decoded and sent to the output. In DRAM, for example, this entire row could be 2 kilobytes. It's relatively large. And of course, the memory is sized such that you can get a good access time as well as good capacity ratio within the chip. So I'm going through many concepts. Feel free to stop me anytime if you have questions, but these will be basics for now. So we also want the memory hierarchy because we want both fast and large, right? We can actually build memory with banks, but we want to have the access time both fast and we want large capacity. But we cannot achieve both with a single level of memory, however much we can bank it. Because as you add more banks, you introduce overhead, which is figuring out which bank to access as well, right? The idea here is to have multiple levels of storage, basically progressively bigger and slower as the levels get farther from the processor. And ensure that most of the data that the processor is operating on is kept close at the fast level. And you're very familiar with this idea, right? Basically, you have register files within the CPU. You have caches that are small but fast. And as you go progressively far away from the CPU, you get bigger memories that are slower but also higher capacity. And that's the idea of a memory hierarchy. And there are a bunch of trade-offs related to it. We'll mainly focus on this part again. I'll just give you very brief. Hopefully everybody's familiar with these concepts because we're going to use these concepts in building DRAM in different ways also. But basically, the reason this works is the concept of locality, right? Programs have locality. They tend to have temporal locality, for example. Recently accessed data is accessed again over and over. And caching, this sort of memory hierarchy, exploits that fact. It stores recently accessed data in this automatically managed fast memory called cache. The anticipation is that that data will be accessed again soon, and this is the temporal locality principle. It turns out this is a good principle that works in many cases. It doesn't work always, so we'll try to design systems that do not work in this case as well. And actually, if you have one paper to read tomorrow, I'm changing. Read this one. This is Maurice Wilkes' cache paper. It's much shorter. He called it Slave Memories and Dynamic Storage Allocation. It's 3 pages, I believe. You can find it on the web. If you cannot, send me an email. But this is what he had in mind when he designed. Actually, he was not the first one. There's another paper that's not as clear in terms of its insight that talked about caches. But he says basically users discussed of a fast core memory of 32,000 words as a slave to a slower memory of, say, 1 million words in such a way that in practical cases the effective access time is nearer that of the fast memory than of the slow memory. So I'd recommend this paper. Everybody should probably read this paper. It's very fundamental. But anyway, that was temporal locality. The other reason why memory hierarchy works is because we can actually bring larger chunks. When we access a row, for example, that's a large chunk. And why don't we bring a larger chunk than we need, actually? If we're needing 4 bytes, maybe we should bring the 64 bytes that's around it. And this makes sense because of the spatial locality principle. Basically, nearby data applications, whenever they access some data, they also access nearby data. And if you actually organize your data such that this becomes more probable, this makes even more sense. And as a result, we usually store addresses adjacent to the recently accessed one in automatically managed fast memory. We have cached blocks rather than managing cache in words. And this is a spatial locality principle. Basically, nearby data in memory will be accessed in the near future, and there are many reasons for it. And one of the first processors that implemented cache, the IBM 36095, it's again another beautiful paper from IBM Systems Journal in 1968 that talks about the design of the System 360 Model 85 cache, and it talks about the spatial locality principle. Morris Wilks didn't talk about the spatial locality when he talked about the caches. Okay, very briefly, a note on manual versus automatic management. This is again orthogonal to what we will cover, but it's also good to keep in mind. Basically, manual management, programmer manages data movements across these levels. You have this cache and main memory. Who puts data into the cache? This is too painful for most programmers on substantial programs, and going forward, as systems become much more complex, and I believe this will become even more painful. But this, people do this. This has been done for a long time. In the 50s, there was core versus drum memory, and programmer managed the core memory. This is still done in embedded processors, but increasingly, even embedded processors are moving into automatically managed caches. Automatic management, hardware manages movement across levels. This doesn't have to be hardware. It could be the software layer also, a simple software layer that doesn't introduce a lot of overhead. But the key is it's transparent to the programmer. And the programmer's life is easier. One simple heuristic that has worked well, that Arvind touched upon in his lecture earlier, is keep most recently used items in the cache. That's the LRU principle, right? Least recently used principle. Although sometimes random replacement works nicely too. It'd be good to understand actually when it works and when it doesn't work, and if we can actually evaluate it well. The benefit of the automatic management is the average programmer doesn't need to know about this, right? The downside is if you actually don't design your program such that they operate this way, then you have a problem. Perhaps you don't get good performance. That's why if you want to have a fast program, maybe you should really know about it. But I think that's a fact of life that we'll hopefully deal with better as we go into this. So keep this in mind. We'll design a DRAM that actually caches portions of the memory rows within itself to improve access latency in the next lecture. Okay, I guess this is I'm making you read this paper even though you I've assigned it. So this is a beautiful paper, as I said. Take a look at it. So when Morris Wilks talked about caches, he talked about automatically accumulating to itself words. So it was automatic management at the time. So when we talk about caches, it's really automatic management today. And if it's not automatic management, it's usually either a scratch pad. A register file is actually kind of a form of a scratch pad, right? You have a level of memory that's exposed differently from another level of memory to the programmer. And you can introduce another level of memory here, which is another scratch pad down there. So this is a memory hierarchy. A modern memory hierarchy looks like this. I'll not go over this in detail, but our focus will be over here, and maybe a little bit over at the merging of memory and storage as well. Any questions? Am I going too fast? No? Everybody's so numb that it's not clear. But okay, let me go over the DRAM subsystem basics a little bit. and hopefully we'll finish with this. So when I think of DRAM, I think of something like this. It starts with this basic cell over here, and you build things on top of it. I'll cover this from bottom up first. We have this bank abstraction, right? And let's start with that bank abstraction to build this, what some call 5-dimensional system, although I'm not sure if that 5-dimensional is correct, given these different dimensions that we have. So today what we have is page mode DRAM, and I'll explain what that is. It's an unfortunate name, I think. But a DRAM bank is a 2-dimensional array of cells, rows and columns. Remember that picture that I showed you earlier? A DRAM row is also called a DRAM page. This has nothing to do with a virtual memory page. So we have sense amplifiers that sense the entire row, and these are also called the row buffer. Some people call the page buffer also. Each address that you send to DRAM is a row, comma, column pair. And you can have the bank address specified as well, of course. If you access a closed row meaning the row is not in this row buffer, you need to send an activate command to open the row from the bank. Then this places the row into the row buffer, senses it. And then you send a read-write command, which reads or writes a column in the row buffer. And then once the access is done, you need to send a pre-charge command to close the row and prepare the array for the next access. You can send a bunch of read and write commands while the row is within the row buffer. And later, if you want to do another access, you have to pre-charge the array. Pre-charge meaning it moves the bit lines to a reference voltage so that the next access can be sensed. If you are accessing an open row, which means that you've already done the activate, then all you need, there's no need for this activate command, which means that an access to an open row is much faster than an access to a closed row. Let's take a look at this pictorially. This is my pictorial abstraction of a DRAM bank. You have columns and rows. It's a 2-dimensional array. And you have a row buffer, which is needed to sense the entire row. Initially, this is empty. And let's say the processor has some accesses. The memory controller needs to access row 0 and column 0 within this bank. Because the row buffer is empty, the memory controller first needs to activate row 0. So it sends an activate command to row 0. Basically, the DRAM bank brings the row into the row buffer. That's bit lines driving the sense amplifiers. And after some point, the values in the row buffer stabilize. And the row buffer is essentially an SRAM row. Basically, you have cross-coupled inverters that amplify the charge that is within the DRAM row. And later, the memory controller needs to read column address 0, which means that it sends column address with a read command to DRAM bank. And the DRAM bank muxes out the appropriate column and sends it back to the memory controller. Later, let's say the memory controller with processor, yes?
Does this procedure have something to do with what happens on modern buses, where you have burst reads and burst writes?
Yes, that's right. So you have burst reads and burst writes because you can burst out of this row buffer very, very quickly. You can basically pipeline the accesses that go to the row buffer. That's what's page mode DRAM. Thank you. So when the memory controller needs to access row 0 and column 1, it can actually pipeline those accesses, basically. This is called a row buffer hit. And in this case, the memory controller doesn't need to send an activate command because the row is already here in the row buffer. And the memory controller only needs to send the column address. As a result, the DRAM chip responds with the data. So this was much quicker, right, the row buffer hit. Let's say the memory controller needs to read the same row, but another column in the same row. Again, this is a row buffer hit, and the controller needs to send only the address, column address, and the DRAM chip responds with the data. Let's say the memory controller needs to access row 1. In this case, this is called a row buffer conflict. There's circuitry in the memory controller that checks which row is open, and the memory controller knows that it cannot access this row. What the memory controller needs to do in this case is to pre-charge the array, which basically gets rid of this row over here in the row buffer, and then activate row 1, which activates the row, places into the row buffer, and then the memory controller can send the column address for that row, and the DRAM chip responds with the data. So this took much longer, right? A row conflict access takes much longer than a row hit access in a bank. So keep this in mind. We'll get back to that. The DRAM chip itself consists of multiple banks. And today, people use 8 banks, but there's no reason to stick yourself to 8. There are many trade-offs related to that. But banks share command address and data buses. And the chip itself actually has a narrow interface so that the costs are low. you get 4 to 16 bits per read. And this is, just to give you an idea, this is an old data sheet from Micron, I believe, but this is a 1 gigabit DRAM chip. And it consists of, this is the memory array that I showed you over here. This is bank 0. It has the sense amplifiers, and this is the column logic. And these are the row decoders, row addresses. And you actually get data, I believe 8 bits of data out of this chip. You can study these DRAM data sheets. They will not tell you a whole lot because they're a little bit cryptic. But I'll give you some references that will hopefully demystify some of the operation of DRAM. DRAM rank, multiple chips are operated together to form a wide interface. We have a small interface in the DRAM chip, right, 4 to 16 bits, to minimize the cost of the chip. But we want a lot of data together. So we actually gang together these multiple DRAM chips that respond to a single command the same way. All chips comprising a rank are controlled at the same time. This is like a rank of soldiers, right? You say left foot, they bring you the left foot. That's exactly what these chips do. They share address, command, and data buses. They share address and command buses but provide different data. And a DRAM module consists of one or more ranks. For example, a dual inline memory module, which I'll show you later, can consist of 1 or 2 ranks. And this is actually what you plug into your motherboard. For example, if you have chips with 8-bit interface, if you want to read 8 bytes in one shot, you put 8 of these chips together, and they all give you a different 8 bits. So you get 64 bits that way. And this is a pictorial example. Basically, each chip can give you 8 bits, and with 8 chips, you can get 64 bits. And this is another way of looking at it. So this is a 64-bit wide DIMM. So even this is a trade-off that people have made, because you're actually reading large amounts of data, a cache block, for example, 64 bytes. You want to increase the interface. The advantage is now you get higher capacity and wide interface at the same time, right? Because you put everything in a DIMM. Also, the memory controller doesn't need to deal with individual chips now. It can deal with multiple chips together to get a lot of data. Otherwise, it would have to deal with individual chips to get different pieces of data. But there's a disadvantage here as well. It's good to keep this in mind. We've increased the granularity of access by having this DIMM. We've increased the granularity of access to 64 bits instead of 8 bits or 4 bits. What if we just needed a word, right, a smaller piece? And there's some interesting work that's being done in the field from Professor Matan Erez's group. And I believe I point to it in my paper. So I'd encourage you to take a look at that. In adaptive granularity memory systems, how do you adapt the granularity of this DRAM system? Okay, so we've not stopped here. We can have one DIMM, right? Now, what if you want to add more capacity? Well, you can have multiple DIMMs and interconnect them in some manner, right? This is a terrible picture here, but there can be some interconnect that interconnects a bunch of different DIMMs together to get a higher capacity DRAM. But now, of course, with that interconnect, your latency increases to different DIMMs, right? The advantage is it enables even higher capacity, and this is one of the main forms that we get capacity today in DRAM systems. The disadvantage is the interconnect complexity and energy consumption can be high. And also you get variable latency. You don't have to get variable latency. You can assume the worst case latency, but then your latency increases, right? Okay, DRAM channels. Each channel basically can contains a memory controller that basically controls a set of DIMMs. So this is one example. Again, this may not be visible from the back. But you can have independent channels where you have multiple memory controllers that are logically independent from each other. They contain a totally different set of address spaces. Or you can have dependent lockstep channels. You have one memory controller with a wider interface. It's another way of getting wider interface. Okay, this is, I guess to put things together, this is a generalized memory structure. Basically, you can have a memory controller controlling a channel consisting of multiple DIMMs. Each of this is a DIMM. And each DIMM actually can have different ranks. In this case, I show you a DIMM with one rank. And then within each DIMM, you have these different banks. And within each bank, you have columns and rows. And a number of consecutive columns form you the cache line. So this is, I believe, the 5-dimensional structure of DRAM. And this is another way of looking at it. If you actually want to know exactly how the internals of the bank operates, you can take a look at this paper. And I'll cover this in a little bit more detail later on. This is the paper my student Yoongu Kim published at ISCA in 2012. Okay. Let's take a look at the same thing from the top-down view. I've covered it from the bottom up. but it's always good to look at it from the top down also to see how this fits. Basically, we've started with this row column and built up to the channel. Let's start with the channel first. If you look at what you have today, it doesn't have to be an Intel processor, but this happens to be the example here. You have some memory connected to it, and it can have multiple memory channels. In fact, I believe i7 contains up to 3 memory channels. And each channel can have multiple DIMMs, and this is one DIMM over here. And one DIMM looks like this. You can take it and look at it. Basically, it can have multiple sides, and each side can be a rank. And a rank is a collection of 8 chips. Each rank shares the address and command buses because they respond to the same thing with different data elements. And they share the data bus. Over here, it's just muxed out. Let's break down that rank. This is the rank that we have. And each chip provides different pieces of the 64 bits. And let's take a look at that chip itself. If you take that chip that consists of multiple banks over here, which can provide independent pieces of data. And if you look at a bank itself, the bank is a two-dimensional array of cells that we've looked at before. And you have a large row buffer. And I believe that's, and if you break this down, break this column down, you'll see the cells. Maybe I should have gone to the next step. But that's the idea. So that's the DRAM system. Once you have the system, how do you transfer a cache block? That's relatively simple once you have this, right? You have this physical memory address space, and you have some 64-byte cache blocks, let's say, within that address space. This cache block is mapped to a DIMM over here and a rank of that DIMM. And if you look at it in a little bit more detail, this is where that cache block may be mapped to, right? Basically, you get 64 bits from these different chips, and the first 64 bits get mapped to row 0 and column 0 of each of those chips. So you get the first 64 bits when you do the access, and then the burst mode provides you the next 64 bits after that, and then the next 64 bits, and the next 64 bits, and the next 64 bits. That's how you keep reading a cache block. Basically, a 64-byte cache block takes 8 I/O cycles to transfer if you have a 64-bit wide bus, in this case. And during the process, you read 8 columns sequentially, assuming your data is mapped this way, which we will briefly talk about, data mapping as well. Okay, so there are a bunch of latency components in this access, obviously. If the processor needs to access DRAM, there's a lot of latency involved in this, and this is something we're going to try to optimize. First, the CPU needs to send to the controller itself, the memory controller itself, the data, the address that it needs. Controller itself has some queuing and scheduling delay because there may be other cores that are accessing memory at the same time, and these requests get queued. And there's a reason for this queuing because the memory latency is much longer than the latency at which the accesses are generated and come to the controller. And memory bandwidth is also much smaller than the bandwidth at which the access can be generated in the on-chip cores. So there's queuing that happens, and the access that comes in is converted to basic commands. And later, there's some transfer time between the controller and DRAM. The controller says to DRAM, I would like this data. That takes time. And the DRAM responds. There's a DRAM bank latency, which is a big part of this latency, actually. And the DRAM bank latency is, again, variable, right? It could be simple column address. If the row is open, right, you just need to send read or write command. It's the row hit. It's called the column address strobe also. It could be, basically in the worst case, I'll skip over this, but in the worst case, if it's row conflict, you need to do a pre-charge, activate, and a column address strobe. And that's the longest latency that you get once you access the DRAM bank. But there are other latencies over here, which we will talk about. Later, the DRAM needs to transfer back to the controller the entire cache block, which takes some time. Depends on the width of the on-chip buses and frequency, as well as the bus latency. This is the DRAM to controller transfer time, so this takes over the bus, depends on the bus width. And later, the controller needs to transfer back to the CPU, right, all the data that it's gotten. So this takes a long time, and we'll look at how to reduce some of its components. A little bit on multiple banks. Basically, if you have multiple banks, you enable parallel accesses, right? And you can also have multiple channels to enable parallel accesses. One key issue in both cases, which bits in address do you use to address these banks or the channels? Multiple channels are better because they have separate data buses. This increases your bus bandwidth, right? Multiple banks, normally in DRAM at least, they share the data bus. As a result, you can get a bus conflict between different banks. So multiple channels actually enable more concurrency. If you want to enable even more concurrency, you would like to reduce bank conflicts and channel conflicts. And people have looked at this problem for a long time. There are many fundamental papers that try to get the best out of the memory bandwidth. One of them I would recommend is Bob Rao's paper in ISCA 1991, I believe, pseudo-randomly interleaved memory. He looks at a lot of different ways of permuting address bits to minimize the conflicts that you get in an interleaved memory by trying to maximize the randomness. But this is again very fundamental, and we'll try to reduce this as much as possible. Ideally, you would like to have infinite number of banks and infinite number of channels, right? But obviously, that's high cost. So given that, how do you actually select or randomize a bank channel index in this address? Usually, lower order bits have more entropy, and you can use randomizing hash functions to minimize these conflicts. And that paper that I mentioned, Bob Rao's paper, is a good one to read that talks about that. So how do multiple banks help? This is very basic, so I'll go over this very quickly. Basically, if you have a single bank, this is what happens. Accesses are serialized. If you have multiple banks in DRAM, you can pipeline those accesses. You can send the address to one bank, immediately after address to the other bank, immediately after address to the other bank, and you get the data in bursts in a pipeline way. And if you have multiple channels, basically you have replicated address and replicated data buses. As a result, you can send all of the addresses in parallel and get all of the data in parallel. That's how you improve parallelism. So we'll get back to this when we talk about bank conflicts in DRAM and how to design a DRAM that has the benefits of more banks without adding more banks. So address mapping is important. There are two major ways in which address mapping is done in today's DRAM systems. Basically, this tells us at what granularity of our addresses interleaved across the different banks. And row interleaving is one way of doing it. In this case, consecutive rows of memory are in consecutive banks. You could think of a row, let's say, in this case, I believe, I don't know what it is. Let's see. Row is 14 bits. Column is 14 bits. So a row is 2 kilobytes. So 2 kilobytes, consecutive 2 kilobytes of physical address space are in consecutive banks. Cache block interleaving, in this case, consecutive cache block addresses go to consecutive banks. And you could imagine different kinds of trade-offs that happen in this case. In this case, perhaps the operating system can control where a row goes. In this case, operating system cannot control exactly which bank an entire row goes, right? Because the cache blocks go to different banks. In this case, access to consecutive cache blocks can be serviced in parallel, though, whereas here they serve pipeline. I'm going through this relatively quickly just to give the basics, but feel free to stop me if there are any questions. Are these too basic for everyone? No? Okay, good. Okay. So this is a choice that the memory system designer needs to make. And I think going forward, looking into techniques that trade-off between these two becomes interesting. The difficulty is, once you try to change the interleaving mechanism, you're really changing the data layout. And there can be a lot of overhead in doing so. One thing that a lot of memory controllers today actually do is mapping randomization. Basically, they do not take just some number of bits from the address. And they normally do not take the consecutive bits from the address. But what they do is they take non-consecutive bits, and they also do some randomization within the address. They take some other bits and randomize the bank index. And the goal is, again, to minimize the potential of bank conflicts. This is a very simplified version of that Bob Rao's ISCA 1991 paper that I mentioned. There he looks at very complicated mechanisms to minimize the bank conflicts, but modern memory controllers, at least many of them, try to do this to minimize the bank conflicts. So this becomes a bigger issue as you add more channels. So I've enumerated some portions of address mapping if you have multiple channels. Then the question is, where do you put the channel bit, right? Do you interleave cache block addresses across the channels? This cache block 0 goes to this channel, cache block 1 goes to this channel. Or do you do something else? Do you do row interleaving? Or do you put half of your physical address space on one channel and the remaining half consecutively in the other channel? There are a lot of trade-offs associated with it. And I'll not cover that, but this is something important to think about. This is a problem that has not been solved very well, in my opinion. How do you actually map the data to the DRAM topology itself? And one of the reasons it has not been solved is DRAM topology itself is not exposed to the operating system today. So operating system has no idea, absolutely no idea where an address, a virtual address, or a physical address gets mapped to in the DRAM topology. But it can influence where an address gets mapped to in DRAM. You can actually write a program that reverse engineers what the DRAM topology looks like. And if you're interested in this, that's a very good way of getting started, getting your hands dirty with the DRAM system and figuring out what's happening underneath. But basically, we have this virtual to physical address translation, a virtual memory-based system. And operating system can now influence where an address maps to in DRAM. So for example, if you have your physical address, if you have your bank bits coming from this set of bits, operating system can influence which bank a virtual page can get mapped to during this virtual to physical address translation. It can say, basically, it can perform page coloring to minimize bank conflict. It can say, for example, it can try to allocate different applications pages to different banks or different channels, right? Because it knows the virtual addresses coming from different applications, and it knows, assuming it knows which bank a physical address maps to, it can allocate two applications to different channels or different banks such that their bank bits are different, right? That way you can separate two applications. And we'll talk about, hopefully we'll talk about a paper that tries to do this in an intelligent way such that applications that harm each other if they interfere with each other in memory are mapped to different channels. But this can become much better going into the future if the topology, if these bits, today the operating system doesn't know which bits actually determine the bank, which bits determine the channel, which bits determine the rank. If that's exposed to the operating system, you can do much better than today. Okay, we still have some time. So one important issue, I'm switching gears a little bit, one important issue we'll cover is DRAM refresh. And we already talked about it. The problem is the DRAM capacitor charge leaks over time, and the memory controller needs to read each row periodically to restore the charge. What does it mean to read each row periodically? Basically, the memory controller needs to activate the row and then pre-charge the row. It doesn't need to actually do a read, because activating the row actually refreshes the row. Because what it does is it brings in the values of the cells, and those values get amplified in the sense amplifier, and the sense amplifier drives the cells. As a result, you've actually refreshed the cell just with an activate. But you have to do a pre-charge because you have to prepare the array for the next access. So that's the refresh. And typical N today is every 64 milliseconds, every row in DRAM needs to be refreshed. And you can do this calculation, right? If you have a 32 gigabyte DRAM system, and each row is 2 kilobytes, how many refreshes do you need every 64 milliseconds? That's an easy question, but you can do the calculation. That's a lot of rows that need to be refreshed every 64 milliseconds. 32 gigabytes, let me try to do it. 2 to the 35 divided by 2 to the 11, right? So that's 2 to the 24 rows that need to be refreshed every 64 milliseconds. That's a lot. So there are many implications of this. I'll talk about how it's currently done. Basically, DRAM bank is unavailable while refreshed. Actually, in today's systems, to simplify the system, the entire DRAM rank becomes unavailable unless you're using a mobile DDR system where the DRAM bank is unavailable only. This leads to long pause times. If you actually refresh all rows, all of those 2 to the 24 rows in 64 milliseconds, you get a very long pause time, right? There are two forms of refresh. That's burst refresh. If you do all rows refreshed immediately after one another, people do not use this anymore for a good reason, and I'll show you that. The other option is to do distributed refresh. Each row is refreshed at a different time at regular intervals. And the difference is over here. This is from a Micron technical note that was published in 1995, I believe. But basically, the burst refresh looks like this. You have a refresh cycle, and during that refresh cycle, the memory controller sends refreshes to all rows. Every 64 milliseconds, this happens, and it takes it for a while. This is bad because you have a bad quality of service impact on the application. Right? Whereas distributed refreshes, you basically stagger the refreshes for different rows so that you're doing a refresh regularly, but you're still maintaining correctness. And that's the idea. Today, most systems use distributed refresh because it eliminates long pause times. One question that I will ask, and I think this is a great research topic going into the future, how else can you reduce the effect of refresh on performance? Can you actually reduce the number of refreshes, or can you do something else? Can you overlap these refreshes with something else? And I'll talk about a couple of potential solutions that we have developed. There are other downsides of refresh. This is just to get you thinking for tomorrow. Energy consumption. Each refresh consumes energy, and you're doing this unnecessarily. Well, the only reason is to maintain data. Actually, you're doing it very necessarily, right? You have to do it if you care about the data that's stored there. Performance degradation, I already talked about this. There's a quality of service impact. You get pause times during refresh. You cannot access that bank or rank. And if that you have a critical request from an application, you cannot satisfy that because you have to refresh that bank, right? Okay, and actually refresh rate limits DRAM density scaling. As this size reduces, what happens is this becomes unreliable, and this becomes leaky. So refresh rate tends to increase, as well as you increase the capacity of the DRAM system, you add more rows, and you increase the refresh count that you need to do. As a result, this limits the DRAM density scaling, and I'll show you some data in the next lecture that shows this. Okay. We're still going over the basics. We haven't talked about memory controllers fully yet. Let me go into that a little bit. Just to preface this, long latency memories actually have similar characteristics that need to be controlled. Memory controllers are not only in DRAM, they're also in flash memory. And the following discussion that I will talk about memory controllers is an example that takes DRAM as a case study, but there are many issues that are similar in other types of memories. For example, flash memory. Flash memory has very sophisticated controllers today. Other emerging memory technologies need to have similar controllers. Phase change memory, spin transfer torque, magnetic memory that we will very briefly talk about. There are many functions of a memory controller. First, in DRAM, you need to ensure correct operation. Actually, in any type of memory, you need to ensure correct operation. In DRAM, it amounts to refresh and timing. The second is to service DRAM request while obeying timing constraints of the DRAM chips. And there are many constraints. If you look at the organization that I described earlier, you can have resource conflicts at many levels: bank, bus, channel, rank. There are delays that I didn't talk about. For example, after you do a write to DRAM, you cannot do a read for a while because the circuits need to stabilize. And there's write recovery latency, write to read turnaround time, read to write turnaround time. And the memory controller needs to obey these. And it also needs to translate requests to DRAM command sequences to obey these different constraints. We'll talk about some of these constraints very soon. Third, it needs to buffer and schedule requests to improve performance. It needs to do reordering of requests to maximize performance. It needs to manage these row buffers that we discussed. It needs to manage the policies. How long do I keep a row buffer open? Right? It needs to manage the bank, rank, and the bus. And finally, if this is not enough, it needs to manage the power consumption and potentially the thermals, depending on what kind of DRAM you're managing. Right? In a 3D stack DRAM, you may need to manage the thermals. In commodity DRAM, this is not a big issue today, but power consumption is a big issue. So it needs to figure out when to turn on or off DRAM chips and manage power mode. So this is a lot of things to manage for a DRAM controller. One thing, very briefly, as an off, we'll go back to this DRAM controller. Where do you place the DRAM controller is an issue. It has been an issue earlier. You can put it on the chipset off the processor chip. The upside of this is you can have more flexibility to connect the processor with different kinds of DRAMs, right? Or different kinds of memories even. And this also gives you less power density in the CPU chip. You don't put the controller as another logic on there. If you put it on the CPU chip, you get reduced latency for main memory access. And this has been done in many multi-core chips today. And also, it enables more communication between the cores and the controller, and we will see the benefit of this today. The cores can communicate a lot more information to the controller because you don't need to use pins now, because the controller is on chip. Right? And we'll take a look at that. What does a DRAM controller look like, a modern one? This is, assuming an on-chip memory controller, you get basically requests from different L2 caches. They get communicated to these different banks. We're assuming that each bank has a request buffer. It doesn't need to be this way, but many of today's controllers have separate request buffers for different banks, at least high-performance controllers. And each bank can have a scheduler, and the purpose of that scheduler is to pick the request that is to be scheduled next. And these different bank schedulers arbitrate with a single bus scheduler because the bus is shared between those banks. The address, command, and data buses are shared. And as a result, you have a priority-based scheduler that picks one request for each bank, and another priority-based scheduler that picks one request from the different banks. And of course, this is simplified because there needs to be other things that this takes into account, writes and reads, for example. Because of write-to-read penalties, the schedulers try to optimize the mode in which they do writes. So they do bursts of writes and then go back to reads, and then bursts of writes and then go back to reads. And you need to, of course, handle refresh over here as well. Yes?
I see on the top line, there's a n times n crossbar, I suppose.
Yeah, so this doesn't need to be a crossbar. This is just...
How big would n typically be?
So for example, I'll give you an example from Niagara. Sun Niagara had 8 cores, actually 8 L2 cache banks, and I believe 4 memory controllers. So it was an 8 by 4. But going forward, and this is just an example, going forward, on scale, this is an important problem. And that's exactly the reason why interconnect is really a part of this course. Absolutely, absolutely, yes. Okay, some scheduling policies. Old controllers used to do first come, first serve, which is not a scheduling policy. It's really first come, first serve, right? It's FIFO. At some point, it's a scheduling policy, but oldest request first. Many controllers today use some form of this, which is first ready, first come, first served. The idea is to, because row hit requests can be serviced much faster, prioritize those requests over others. That's the first priority level. The second is prioritize older requests over others. So you form a priority level for each request. That takes this into account. The goal is to maximize row buffer hit rate with the anticipation that this will maximize DRAM throughput overall, because you get much lower latency and you utilize your data bus much more often as well. And actually, the scheduling is done at the command level, right? You don't actually do the request level. You basically have the column commands, read and write, prioritized over row commands, activate and precharge. This is just something to keep in mind. You could do it at both levels, but this is something you can keep in mind. A scheduling policy is essentially a prioritization order. And this prioritization can be based on many things, and I'd encourage you to think about some of these things. There are a couple of papers in this year's ISCA that talk about using other types of information in request criticality, and we have some papers that I will go into using other types of information. You can use request age, you can use row buffer hit miss status that current controller use. They use request types also, but an important problem is how do you actually prioritize prefetches, reads and writes over each other. And these all have an important effect on performance because the latencies are very large at that level. A requester type. Do you prioritize load miss over store miss? How important the request is? Is it the oldest request in the core? What application is the request coming from? So we'll cover some of these going into the future. But there's a lot of research that needs to be done to understand this in a good way. Yes? I couldn't hear very well. Yes. That's right. So if you can perfectly randomize and there's no queuing delay, then you don't need to do any reordering, I think. But the problem is you cannot perfectly randomize. I think both of these need to be done. I agree with you. If you need to do both to get the best out of the system. The problem is you have a limited number of banks. Oh, can this contradict the effort? So the controller knows the randomization it does, right? It has the addresses. But once you have conflicts, the only thing that you can do is reordering after that point. Yeah. I don't think it will contradict the effort. But if you can avoid reordering, I think if you can design a low-cost system that can avoid reordering, that's the best. The problem is I think it's very difficult to achieve that. Okay, so row buffer, I guess we have a few more minutes. I'll briefly cover these basics also so that we can go into more detail. Row buffer management policy is an important policy for a DRAM controller also. Basically, do you keep the row open after an access or do you close it right away? Open row policy says keep the row open after an access. The upside is next access might need the same row. In this case, it'll get a row hit. The problem is if the next access needs a different row, you get a row conflict, wasted energy. You shouldn't have kept it open. The other policy, closed row policy, that's employed in many controllers, you close a row after an access, assuming there are no other requests already in the request buffer that need the same row. So you actually scan the row buffer to figure that out with some logic. The upside is next access might need a different row. This way you avoid a row conflict. You prejudge the array earlier. Whereas if the next access needs the same row, then you have an extra activate latency. So you have a trade-off now. Do you use the open row policy or do you use the closed row policy? And open row policy is good for applications where you have good row buffer locality. If you're streaming through the row, for example, you get very good row buffer hit rate if you use the open row policy. Closed row policy is good for applications that are more random access, if you keep accessing random locations. Yes?
The access are just read access. Does it mean to keep open? Like if you close it, you have it in the buffer. Like you just want to read them, so you don't, it doesn't matter if you close or not.
But remember, the row buffer is large. It's 2 kilobytes. If you just want to read 64 bytes, yes, you might want to close it. But what if you're going to read sequentially within that 2 kilobytes? Right? If you need more stuff from that row, you would like to keep it open, regardless of whether or not there are reads or writes. So this is orthogonal to reads or writes. Okay, so there are adaptive policies that many controllers actually use today. They try to predict somehow whether or not the next access to the bank will be to the same row, and they try to adapt the policy based on that. But this is, again, another area that's open for improvement, I think. How do you actually manage the row buffer in an intelligent way? I'll leave this to you to study. But let me briefly talk about why these controllers are difficult to design, and then we'll adjourn for the day. And I'll take questions. Basically, why are these controllers difficult to design? I've given you lots of complexity in the controller, right? That's part of the reason why they're difficult to design. They need to obey these timing constraints for correctness. And there are many of these timing constraints, 50 plus. If you look at a DRAM data sheet. Write to read delay, minimum number of cycles to wait before issuing a read command after a write command is issued is an important constraint. You need to keep track of many resources to prevent conflicts. And I've given you examples of these resources. You need to handle DRAM refresh at the same time. You need to optimize for performance in the presence of all of these constraints. And reordering turns out it's not that simple, especially if you want to have a large request buffer. And predicting the future is not that simple. Ideally, you would like to predict the effect of what you do in the controller. How does that change the performance that you get into the future? And actually, the decisions you make affect the long term significantly. So for example, you may want to send a request to the row buffer right now, but that may not be a good option, right? If the row buffer is open, and if you have a request that hits in the row buffer, you may think right now, at this point in time, if I send this request, I get lower latency. But what is the implication of that, I don't know, maybe 2 milliseconds from now? Maybe what you've done is you've delayed some other core that's waiting for a critical request. And by optimizing that DRAM bus bandwidth at that point in time, you're actually reducing system performance because some other core couldn't get its request. And as a result, what happened is it couldn't finish its scheduling quantum, and it needs to be scheduled again. So it has a long system level effect, right? How do you actually understand this? I think in this sense, some of these design decisions that you have in the DRAM controller ties nicely with what Arvind was talking about earlier. How do you model this? And how do you look at the effects of this in the long-term system behavior? It's not that easy, I think. And Arvind asked many interesting questions that I empathize with. But what are these DRAM timing constraints? If you're actually interested in that, this is only, I think, 1, 2, 3, 4, 5, 6, 7, 14 of those. And these are actually important constraints. Write recovery latency, for example, takes 12 DRAM cycles. That's a lot of DRAM cycles basically, you need to, DRAM controller needs to decide, do I actually switch to a mode where I do a write? Because that leads to these write recovery latencies. That leads to, if you want to exit from that route, you need to wait for 6 extra cycles. And these are dead cycles. You cannot do anything in DRAM while these 6 cycles are happening. Okay, so if you would like to learn more about DRAM operation, I wouldn't recommend the data sheets. Data sheets are good, but they do not tell you the underlying reasons of why these things happen. But you can take a look at these papers. These tell you why these DRAM timing constraints actually exist. So I'd be happy to talk more about these. And I think I'll stop here right now and take any questions that you may have. And the next lecture we'll start with, now that we've covered most of the basics, we'll start with how can we actually do better? How can we design simpler controllers? How can we design DRAM where we can overcome some of these scaling issues that we're seeing? Yes?
To introduce the question, does HP
HP there means Hewlett Packard. Oh, HP. No, this is the. So this is my way of reference. This is a high performance computer architecture conference. Yeah, that's where the paper appeared.
Do you know
Cacti, yes.
Does that cover DRAM or?
So I believe Cacti does have a model that covers 3D stacked DRAM. I do not believe that is a model that covers commodity DRAM. Not commodity DRAM. Commodity DRAM models, if you're interested, Rambus has an analytical model that was published in Micro 2010.
No, one practical thing that I am interested in is the system C fairly abstract level of the cache hierarchy, and I don't know anybody who has it. Some people say it's in the books, but I don't know what
Entire cache hierarchy that's based on system C.
I have system C. Actually, I only needed the LM to do the model.
Okay.
But I need the whole block of memory parameterizable, and I need to be able to simulate it.
Maybe we can talk offline about this. I'd be happy to try to help. Any other questions? Okay. I guess it's time for lunch probably then. Thanks. I haven't. Thanks.
I need to get your notes.
Oh, sure.
Full of information.
Yeah, I wanted to cover the basics.
Yeah, because we are building now a flash-based machine.
Oh.
So with a lot of ability for in-core computing.
Oh, okay.
In here.
You have it?